Hello everyone. Today I am working on repairing an adapter unit. It is a 12V 10A power supply module, and I will be troubleshooting this specific device for you all today. The customer reported that it does not provide any output power when plugged in. It has an integrated indicator LED. The LED should light up when output exists, but it remains off. I am not sure what equipment this powers, but it seems to be part of a computer system. It likely supplies a component within a driving school computer workstation setup, most probably. I just opened it up, and after a quick check, the fuse is intact and the output diodes are not shorted out. I am making this video to find the fault. I am not sure what is wrong yet. I just opened the casing. The 4A microfuse is there, and testing it shows it has continuity. Typically, the secondary side uses two dual diodes for the rectification process. Testing those dual diodes confirms they are still functional and definitely not shorted out at all. The indicator light turns on, showing stored energy, so there is no short circuit at the output. Looking closely, without removing the aluminum heatsink, this block is there to dissipate heat for the component. Given its high capacity, the unit outputs a full 12V 10A. Because of the high power, I am looking at this oscillation control IC right here. It is a switching power supply featuring a MOSFET to drive the transformer. The secondary side has a coil to provide induced current rectified by two dual diodes to deliver 12V. Naturally, there is a feedback loop using an optocoupler to stabilize the output voltage. This looks like the main bridge rectifier. It handles the AC input. Let me measure it for you. I will disassemble it to check for faults. Blown fuses without output usually indicate specific component failure. The power loss is likely due to a faulty fuse, a dead MOSFET power stage, or possibly shorted output diodes. Before testing, I will use a series light bulb limiter. Watch the light bulb carefully. It will flash briefly, you see? See that? It means the capacitor is fully charged. Measuring this, the DC voltage after the bridge rectifier is present, reading about 297 to 300 volts. Testing output. However, there is absolutely no output voltage. The capacitor likely holds a charge, so I will discharge it safely. See that? It holds a massive charge, quite dangerous. I still do not know the fault. I will open it up now to inspect the components. Another video on repairing a switching power supply unit. This is the adapter unit that I am prying open. The glue is holding it together tightly. Oh wow, something has clearly exploded inside. It blew up the component, the resistor on the MOSFET source pin. Connecting to ground has blown, meaning the circuit is open. The capacitor still holds a dangerous charge. So the power stage has definitely failed. It uses this oscillation IC. Let me check. The 3843 chip is very common in these power supplies, commonly used Chinese components. It is quite widely used. The MOSFET has certainly failed as well, power stage shorted. But the fuse remained intact. A 3.3 ohm resistor was burnt instead. Fuse intact, the fuse did not blow. On the primary side, consequently, the fuse remains intact. Capacitor holds no charge. Now I will proceed to repair this power stage. Using a 3843 oscillator IC, to drive the MOSFET, I will remove it and then troubleshoot the circuit. I have removed the faulty MOSFET. This MOSFET is definitely shorted out internally. All three pins are shorted. GDS are fully shorted, so the power stage is damaged. Let me read the MOSFET part number. The part number is model 11N60. It corresponds to a maximum current rating of 11 amperes and a maximum voltage of 600 V. I will find a suitable replacement. Notice the 0.33 ohm resistor connected to source. Connected to source pin. Current flows from D to S, and it is burned out here. I need to find some spare components. I also suspect that the 3843 EC is dead. Let us check if my suspicion is actually correct. This is an original circuit capacitor. Still installed there. Original capacitor, with manufacturer design labels attached. Use the soldering wire, everyone. These are definitely Chinese components. I will now find some components. Then I will guide you all. Repairing a 12V 10 amp switching power supply unit. Just one single electronic component. I just found a few components to prepare for the repair. I have obtained the IC already. This MOSFET is an 11N60 type. I am replacing it with a 13N60 version. It handles higher current, so it is fine. I suggest using an equal or slightly higher rating. The burnt resistor is this 0.33 ohm resistor. It features orange, and silver color band codes. Silver means the multiplier is 10 to minus 2, so it equals 0.33 ohm. The circuit board has markings printed for you. This board lists a value of 0.47, but they are using 0.33. It is perfectly standard and fine. For this part, I advise everyone to replace it. Use a value equal or slightly higher instead. Do not use a smaller value. I found a 0.39 ohm replacement. Either 0.39 or 0.47 works. We should choose a higher resistance value. The circuit will then shut down sooner. The overcurrent protection will trigger at an earlier stage. It will be much safer, everyone. Suppose we use a 0.22, then the overcurrent protection would trigger too late. The circuit might fail much faster, you see. Therefore, I recommend using the correct or a slightly higher rating. The power rating here is actually very small indeed. I will replace it now because it is small when the MOSFET shorts out. It blows up instead of the fuse. I will show you the steps to repair a power supply unit with a blown power stage for your reference. It uses 3843 IC driving this MOSFET. When this MOSFET fails, notice this. It will certainly fail and burn the source pin sensing resistor. The source pin current path behaves like this. Let me show you this reference. Positive rail is right here, folks. It flows to one end of the main transformer primary winding. It reaches the MOSFET drain pin. The gate receives oscillation pulses from the driving eye controller. It continuously triggers the gate pin. Switching from drain to source creates current variations in this coil. The source pin connects to a burnt ground resistor, you see. It is burnt like this one. The overcurrent protection circuit, it goes through this specific resistor. Then it enters the controller IC pin, dear viewers. I confirm you must also test the resistor connected to the IC pin. Sometimes the overcurrent protection resistor also burns out, because when this part fails, see. When the power transistor burns, high drain voltage spikes to the source pin. It travels forward instead of back. In that instant, it damages the control circuitry. The IC is likely destroyed, so I prepared replacement. Thus, we must inspect everything. Components on this overcurrent protection line. It leads back to this pin, guys. This is actually the third pin, counting 1, 2 to pin 3. It connects to pin 3 of the 3843 IC chip, so verify all components at that pin. I am certain if this resistor burns, damage occurs. The oscillation fails, so I must replace it too. And if the IC fails, I will also check the pins of the PC817 optocoupler. Check for any internal shorts. Often the PC18 optocoupler will also short. Otherwise, the new IC might explode again. Furthermore, the MOSFET shorts its gate, drain, and source together, causing high drain pin voltage. The 300V line connects directly to the G pin. Next, we check the G pin components. These are the components located at the G pin. It leads to the gate. It connects here to reach the trigger pin. Along that circuit path, there is this specific resistor component, 33 ohm resistor, and the reverse diode. Check these components as well. Verify their integrity. I will test them for your reference, checking for any faulty components now. For the PC817, I only need to measure pins 4 and 3. Pins 1 and 2 rarely fail, using the 10K scale for leakage testing. Measuring between pins 4 and 3 shows no leakage. It is fine. Step 1, Step 2, Step 3, Step 4. Measuring 3 to 4 shows leakage, so it's good. Measuring 4 to 3 shows no leakage, all good. So the PC817 is not faulty at all. Next, I will inspect the overcurrent protection resistor on the board. This feeds voltage to the ICE protection pin. I notice this resistor is faulty. The surface of this resistor appears charred and dark. It might be shorted. The IC is likely dead too. The component marking indicates the value. The board indicates 1K ohms. The board labels the component value. Otherwise, we use color codes. Although it is 0.47, they installed a 33. They calibrated it specifically during the design and manufacturing phase to ensure the circuit achieves a precise cutoff point. As you can see, the 1K resistor is burnt. It has no continuity. My multimeter shows good continuity. See, it has resistance. It is burned. Once that resistor has burned out, it is certain that, as I mentioned, if this burns, high voltage cannot return to ground, cannot reach ground. It follows the path and it will destroy the ICE. I am certain the eye failed too. I will remove the IC and replace some components now to see if it works again. If that resistor has burned out, I am certain the seek failed. If the EEC is faulty, don't install the MOSFET yet. We will perform measurements first. After replacing parts and finding faults, we check if there is any oscillation signal present. Check for output oscillation. Installing the MOSFET is the final step. The IC and the 1K resistor are already burned. I will check if the diode is shorted too. Removing the diode lets me test the resistor properly. I am working without a schematic diagram. This 3843 circuit is just like an electric bike charger. I have repaired these before. Regarding feedback circuits, it should output 12 volts. Only the feedback path differs. Actually, this resistor is fine. It reads 40 ohms. It is a 39 ohm unit. The color code is orange, white, and black. 39 is correct, as I measured 40 ohms. The diode runs from the gate back to the MOSFET. Feedback from the MOSFET side. This diode is definitely shorted out. The diode is shorted out. It is a 4-to-148 diode. Testing both ways shows continuity. As I said, the high voltage from the primary, the 300V line, leaked to the gate. It passes through that diode, into the gate driver, into the gate drive pin. Both the IC and parts failed. I will replace those components now. Check if it works fine later, replacing all the failed electronic parts, including 1K and 4148 diodes. The main controller IC and the source pin resistor power on to measure the pulses. Then we will proceed further. Then we will continue again, step by step for your reference. Here is the replaced controller IC. It is a UC3843A1 chip, that is the oscillation IC. And I replaced it already. Replacing all the failed detected components, they include these listed parts. The source pin resistor here, and the pulse snubber diode to lock the MOSFET drive. Parallel with this 39 ohm resistor and the 1K ohm resistor for the overcurrent protection circuit. That overcurrent protection pin is pin number 3, as shown. The output pulse is pin 6. Pulse driving the control IC for the MOSFET gate drive, it is on pin 6. We must install all these parts, measure pulses before installing MOSFET. Now we install the MOSFET. There is one more failed component. I have checked it already. I will show you guys. Take a look at this. My old e-bike charger schematic, the 3843 IC functions similarly here. To be specific for this part, I have replaced this component now, specifically the 1K ohm resistor. Each type has different rated values. We will understand the logic soon. Take this 0.33 capacitor component and this 1K resistor as well. I will bring them back together. Now I will proceed to check voltages before installing the MOSFET. I must check the gate pulse. Pulse must exist before final installation. Actually, based on my recent measurement, no pulse. I found another failure. The failed component is this one. It is the 104 ceramic capacitor. It pulls pin 4 to ground. This is identical to a shorted PC817 optocoupler, pins 4 and 3. Since my previous measurement indicated PC817 pins are not shorted internally, but it behaves like a transistor, clamping pin 4 to the ground to suppress noise. It has failed. Because it is shorted, it effectively pulls the feedback pin 1, the FB pin, to the ground. Thus, the IC stops working completely. It is like excessive current flow, triggering internal current 4 to 3. Triggering this current is the same as a shorted capacitor pulling low, resulting in no gate pulse output. Watch this, I will demonstrate it. So the failure happens because understanding circuits helps find faulty parts. And now I will perform the measurement. Digital meter first, then analog meter. I will power it without MOSFETs, powering through a light bulb test. This keeps the circuit safe today. The bulb is charging the capacitors. Now I will take some measurements. Checking the voltage levels right now. The 300V supply is present here. The 300V line is fully active. Now checking the VCC supply rail. Monitoring the main VCC power source, feeding at pin 7 right here, connected to a filter capacitor here. Limited by a startup resistor path. That resistor is rated 200 kiloohms. It provides startup bias for ICs. Feedback supply is not active yet. This component is the startup resistor. It acts as the startup resistor. At the terminal of this resistor, the 200K resistor connects over here. This point is the supply rail. We have 8 volts present now. The 8-volt rail is active. The 8 volts measured is exactly. The voltage at pin 7 node, once running, the supply will increase. I will show you later on. It reaches 12 to 13 volts. I will measure it for you. Output pulse is not active yet. I set the meter scale now, measuring DC voltage at 50 range. I will check it for reference. VCC 8 volts is confirmed here. Checking the gate drive signal now. Voltage at the gate pin terminal. Testing the gate drive signal now. There is absolutely no signal present. Switching to the AC10 range. Still no gate drive pulse detected because this component is faulty. As mentioned, the 104 capacitor causes a shorted FB pin like a shorted PC18 coupler, thus no pulse is generated. Now I will proceed to replace that specific faulty component to observe the circuit's response. See how the pulse changes. I will discharge the voltage to prevent any electrical shock. Here is the capacitor component. The shorted capacitor is here. Let me show you this path. This is pin number 3, the ground pin for PC8110. This is pin 4. Pin 3 is ground indeed. Tracing along this signal path, it connects to pin 1. That is the FB pin with a 104 filtering capacitor. This circuit uses 104 value. But on this e-bike charger, it is 103 capacitor just for noise suppression, so either 104 or 103 works. Some circuits use 102 capacitors. You can remove this capacitor. It works, but replace it for better circuit stability performance to handle stray noise spikes. Preventing any further operational errors, the board clearly labels 104. The PCB markings are accurate. This is a 104 capacitor. Let me measure for you using the 10K resistance range. I am testing the component. It is shorted. See that? These components are poor quality. Let's find another 1.4 replacement. I will use this larger 1.4. I'll measure it for you now. It will output some pulses. Check if the salvaged part works. All right, I will measure it soon, checking the operating frequency. My meter can measure IC frequency. The 3843 before circuit stabilization. These are just initial startup pulses when it has startup resistance bias. It generates pulses at low frequency. Once the feedback loop is active, everything is working fine now. The output voltage is now stable. It then increases to stable frequency. I will measure that for you. I just replaced the shorted capacitor. Check the FB line and lamp. See, the lamp is lighting. When I plug in the power, I will measure it for you. There is pulse output already here. It produces a low output voltage. Right at the gate pin output, the needle jumps up a little. Measuring A shows active pulses. Higher voltage output is present now, unlike what I measured before earlier. This IC operates at high frequency. The meter shows no needle movement. It remains completely silent and still. Let me use the digital meter. It can measure the output frequency. Take a look at this result. Since the source is only 8V and no FB signal returns yet, this internal IC oscillator is running. Inside the 3843 integrated circuit chip, it generates a low frequency pulse. I think it is measurable here. I will perform a quick measurement, setting the meter to frequency mode. My multimeter can measure that signal. Probing the gate pin right now. It reads 5 kilohertz, see that? Exactly 5 kilohertz is measured. Testing the power supply rail now. There is no frequency detected here. It seems to be floating currently. The reading shows 0 hertz here, and this one is 5 kilohertz. That signal is 5 kilohertz indeed. The pulse is present as expected. Installing the MOSFET into the circuit. Let's see if it runs properly. The MOSFET is currently not installed. The capacitor might still hold charge. I am worried about getting shocked. Use this light bulb for discharge. Found this bulb in microwave ovens. I use it to discharge electricity. Replacing it with this new MOSFET, checking if it operates correctly today. The part number is 13L60 here. The original part was 11L60 instead. This replacement part will provide more. It handles higher current load capacity. Voltage matches, but current is higher, making it a much stronger design. I often upgrade supplies this way. This helps to make it better, increasing the overall component durability now. Removing the circuit diagram for now. Using the 3842 controller IC chips, like the 3843 driving the MOSFET, repairing becomes easier with circuit knowledge. These are applied very widely indeed. Common in electric bike chargers too, or consider these switching power supplies. They are extremely common and popular. They are widely used by everyone. I have installed the MOSFET transistor. With pulses active, I will power, measuring the output voltage right now, still connected via the current limiting bulb. Please observe the light bulb carefully, measuring output voltage while powering on. The indicator light is now on. It is exactly 12 volts now, slightly higher as it is non-standard. The power indicator is already lit. Let's test it with a bulb. This is the adapter output end. Look closely at the output terminals. I will perform a test now, checking for any voltage sag occurring. Still 12 volts under the load. Using a 12 volt 20 watt, this is the power rating specification. Let me test it right now. Everything works perfectly fine as expected. Still okay, burning hot to touch, there are no issues at all. It is getting too hot here. Measuring while the circuit is active, it will have a supply voltage. Feedback keeps the IC running properly, working with sufficient power output levels from the auxiliary secondary transformer winding. That secondary coil inside the transformer, rectified and fed back into circuit, I only measured 8 volts earlier. Due to the startup bias resistor, let me measure it again now. The feedback voltage should be higher. Heavier loads increase the supply voltage. Still only 8 volts measured here. Should I check the component again? I might replace the filter capacitor. The filter capacitor may be weak. It is designed to run at 8V. It shows around 8 volts right now. Will it rise when under a load? I will connect the load now. Let's see if it rises, everyone. This load is a light bulb. The source is still at 8V. Let's plug it in to test. It jumped to 14V, you see. It rises when under a load. When a load is applied, the output is influenced by this specific feedback loop path. The feedback circuit path, everyone. The circuit detects the load, it senses the heavy current demand, and sends back a feedback signal to boost the ICE output power. Increased activity means higher variable current. Flowing through the main primary winding, this compensates for the voltage drop during this heavy load condition now. Because the primary coil is active, it is working very hard now with a stronger variable current flow. The ferrite transformer core produces a much stronger magnetic field effect. This means the output winding rectifies a higher voltage of 14V, everyone. Normally in standby with no load, the circuit stays in standby mode. The ferrite core magnetic field is weak. Consequently, the winding induces only about 8 volts output, everyone here. So I have shown you the repair of this power supply adapter, a 12V 10A unit, you see. Repairing it is quite simple, actually, once we understand the circuit design. Hope you find these videos helpful. Please subscribe for more technical updates. This video ends here for today. Goodbye and see you again soon.